Alright, in today's video we're looking at some practice multiple choice questions for grade 12 chemistry, electrochemistry. These multiple choice questions do not include anything on electrolysis, so be sure you're also studying that separately. So let's jump in. Make sure you have a data booklet with your reduction potentials chart, a calculator, and some scrap paper. The best way to get some good out of this is to pause the video and try each question yourself, unless you've already done them, in which case you can just flip through to find whichever answers you're looking for. So the first question, the oxidizing agent in this reaction. So the oxidizing agent, remember, is the thing that's getting reduced. So we're looking for something where the oxidation number is going down because it's gaining electrons. So let's take a look. The lead on the left at the beginning is the element lead, so it's beginning with an oxidation number of 0. On the right, we have lead sulfate, and in lead sulfate we recognize that's an ionic compound, so we'll start by splitting it into the two ions, lead and sulfate. Some earlier chemistry, sulfate's charge is 2-, which means this lead must be 2+. And that's its charge as an ion, then its oxidation state is +2. So I can tell right now that the Pb, the lead metal, is being oxidized because it is increasing in oxidation state, so it's losing electrons. So this is not going to be the oxidizing agent. The oxidizing agent gets reduced. The lead would have been the reducing agent. So now PbO2, the Pb in there is +4. The O's are -2, there's 2 of them, so the lead begins with an oxidation number of +4. On the right, the only place lead shows up is in the lead sulfate, so here you can see that it is gaining electrons to go from +4 to +2, and that means the lead oxide is being reduced, which means it is the oxidizing agent. Number 2, which of the following is a redox equation? So the very best way to do this would be, again, to look for changes in oxidation states. In the very first example, the hydrogen begins with 0. On the left, it's the element hydrogen, and on the right, in the water molecule, it's +1. That's all I need to see. Since the hydrogen is changing oxidation state, this reaction must be a redox reaction. The hydrogen here was being oxidized. Now if you look at the other choices and you try to assign oxidation states to each one, to each element, you'll see there's no changes in oxidation state in any of the other equations. Question 3, which of the following has molybdenum with the highest oxidation number? So in the first example, that's an ionic compound, so you would think of it as a molybdenum ion and chloride ions. Chloride is a -1 charge when it's an ion, and there's 5 of them attached to the molybdenum, so the molybdenum's charge was +5, or 5+, I guess would be a better way to write that, as its charge, which means its oxidation state is +5. That's a pretty high oxidation state. In the second case, doing something similar, that's also an ionic compound. Sulfide is underneath oxygen on the periodic table, and its charge is 2-, just like oxygen. There's 3 of them, so it's going to be -6 total. So there's 2 molybdenums. Each one of those molybdenums would be +3 as its oxidation state. MoO4 2- would be a complex ion. There's 4 oxides, each one is -2, so 4 times -2 is -8 rather. The entire ion's charge is 2-, so this molybdenum must be +6. And so far that's the one with the highest oxidation number. In the last case, again, we have chlorides, which are -1, their charge. 12 times -1 is -12, so there has to be +12. That's divided over 6 molybdenums, so each one of those molybdenums is +2. So the highest oxidation state was choice C. All right, so question number 4. We're asked which of the following combinations are going to react spontaneously, and that's an important word, spontaneously, it means that the equilibrium constant for the reaction is large. That's one way to think of it. Or that the cell potential for the reaction is positive. That's another way to look at it. So it helps to have a reduction potentials chart in front of you as you're looking at this. There's a quick shorthand way to do this, and I'm going to point that out in just a moment, but the longer way to do this would be to examine each reaction on your chart. So for example, in the first choice, A, we notice that iodine, I2, on my chart is getting reduced. Iodine gains electrons and it makes iodide. And then I find copper 2 plus on the chart, and copper 2 plus also gets reduced and it makes copper. So that first choice has two substances which both would need to be reduced. Neither one of them could get oxidized. To have a redox reaction, you need something to be reduced and something to be oxidized. So that first choice just doesn't make any sense. The second choice is possible. The Pb2 plus could gain electrons and could make Pb. That would be a reduction reaction, while silver, Ag, could lose electrons and become silver positive, and that's an oxidation reaction. So part B is at least possible. So now we'll look at a reduction potentials chart and we'll see what the potential is for each half reaction. Well, for the lead to be reduced, its reduction potential is negative 0.13 volts. Whereas silver, to be oxidized, I have to read the equation backwards on my chart and therefore change the sign of its potential. So the oxidation potential for silver is negative 0.80 volts. And so together the cell potential for this reaction would be negative 0.93 volts. And because it's a negative cell potential, that reaction is not spontaneous. Remember that a spontaneous reaction needs to have a positive cell potential. So this is the long way to do it. You can go through every choice in that same way. The faster way to do it, though, is to remember that little cheat rule that we learned about our reduction potentials chart. When you're looking at the chart, something on the, if you imagine this is the chart, something on the left side of the chart, so something that is being reduced, would react with something on the right-hand side of the chart, which is being oxidized, if it's below it. So for example, something like this pattern, something on the left reacts with something on the right and below it. And that reaction is spontaneous because it has a positive cell potential. When you look at the last example that we just did, the silver and the lead, the Pb2 plus on my chart is on the left-hand side, but the Ag, the silver metal, is on the right side and above it. So for the second choice there, this was the pattern on my chart. The Pb2 plus was on the left, and the silver metal was on the right but above it. And that doesn't follow the pattern that we established. So we could have just said that reaction's not going to happen because it doesn't follow that pattern. Something on the left reacts with something on the right and below it. Just make sure you understand why that pattern works. It just works because when you have that pattern, the cell potentials are positive. So by that reasoning, you could quickly go through these, and you'll notice that the third choice, where zinc 2 plus reacts with magnesium, zinc 2 plus is on the left side of my chart, and magnesium is on the right side and below it, so that reaction will be spontaneous. Question 5, which of these half reactions is not an oxidation reaction? Well, to figure that out, consider the oxidation numbers. So for the first one, Cl on the left has an O with it. The O is -2. The entire thing is -1. It's an ion. So that means that Cl starts off as a +1 oxidation state. +1 and -2 gives me the -1 charge. In the second, on the right-hand side, ClO3 negative, 3 O's would be 3 times -2, -6. The whole thing is still -1, so the chlorine there is +5. To go from +1 to +5, that is an oxidation reaction. We're looking for something that's not an oxidation reaction, so it can't be the first one. In the second half reaction, the H's and the O's are not changing. They're -2 for the O's and +1 for the H's. So it must be the carbons if they are changing. Let's take a look. On the left, there's 6 H's. That'll be +6 total. There's 1 oxygen, which is -2. So I need another -4 because the whole thing is neutral. There's 2 carbons, so the -4 must be because each of the carbons begins at -2 oxidation state. On the right-hand side, we have 2 O's, that's -4, and we have 4 H's, that's +4, so together that's 0. And that means those carbons on the right are 0 oxidation states. To go from -2 to 0, that's also an oxidation reaction, so it can't be 2. Then it must be 3, and let's just verify it. The 2 O's in NO2 give me -4, so the N begins at +4, and on the right, the 4 O's gives me -8, and the 2 N's must each be +4, so I get +8. And so the N's are actually not changing, the O's are not changing. That's not a reduction or an oxidation reaction. Choice C is the correct answer. Number 6, identify the species that is being reduced. And you can see I actually already gave away the answer. Thing being reduced, so let's look at oxidation numbers. The H's are +1 on both sides, the O's are -2 on both sides, so we can just ignore them. It must be the MNs and the C's that are changing, so let's look at the first guy. 4 O's is -8, 4 times -2, so this manganese is +7 because the entire thing has a charge of -1. The Mn on the right is +2, so to go from +7 to +2, that is gaining electrons, and I'm done. Gaining electrons is being reduced, so the permanganate is the substance that is being reduced. A strong oxidizing agent. Well, remember that oxidizing agents get reduced. So in the example up above, the permanganate, which was getting reduced, is the oxidizing agent. Now, if you're a strong oxidizing agent, you must easily get reduced, and reduction is gaining electrons. So look at these choices. A substance which loses electrons readily, easily? No, they don't lose, they gain electrons. Gain electrons readily, readily means easily. That's the one that I'm looking for, I think. A large increase in oxidation numbers. Well, oxidation numbers increasing means it's being oxidized, and we're looking for something which is getting reduced. The oxidizing agent gets reduced. So C and D could not be the answers. Question 8 requires a little bit of reasoning because none of these elements, cadmium, neptunium, palladium, or cerium, are on our table of half reactions in our data booklet, so we can't look there for help. We're looking for the ion that is the strongest oxidizing agent, which again means most easily reduced. Right? The oxidizing agents get reduced. And if it's most easily reduced, it has the highest reduction potential. That's another way to look at it. But again, we don't have the reduction potentials on our chart for these elements, so we have to use some reasoning. It tells us these reactions are all spontaneous, so they happen. So in that first reaction, the cadmium 2+ is being reduced. Cadmium 2+ goes from +2 to 0. So then if cadmium 2+ is being reduced, when it reacts with the neptunium, then we can conclude is that the cadmium 2+ must have a higher reduction potential, since it's being reduced, than the neptunium 3+, right? So the neptunium 3+ could be reduced to make neptunium metal. Cadmium 2+ could be reduced to make cadmium metal. Since cadmium 2+ is the substance being reduced, cadmium 2+ has the higher potential than neptunium 3+. In the second equation, we can see that the palladium 2+ is being reduced as it goes to palladium metal, which is 0. So that means the palladium 2 plus has a higher reduction potential than the cadmium 2 plus. So on our ranking here, palladium 2 plus is higher than cadmium 2 plus because it gets reduced in the reaction with cadmium. In the third reaction, see if you can figure out what we'll conclude there. Since the neptunium is starting off at +3 and ends at 0, the neptunium is being reduced, which means the neptunium has a higher reduction potential than the cerium 3 plus. So the cerium 3 plus is lower than neptunium 3 plus. So we're looking for the substance with the highest reduction potential. That would have been the palladium 2 plus. This kind of question would not be on the June 2020 unit test, our coronavirus test. Questions 9 and 10 refer to this voltaic cell. So we're asked, when it operates, cations are moving in which direction, and we also want to know which electrode is gaining or losing mass. Well, we would need to first look on our reduction potentials chart, and we'll find the half reaction that involves lead and lead 2 plus. We'll look at its reduction potential for lead 2 plus, and we'll also look at zinc with zinc 2 plus, and we'll look at the reduction potential for zinc 2 plus. So finding those on my chart, I notice that the lead 2 plus has the higher reduction potential than zinc 2 plus. That tells me that the lead 2 plus, this half cell, is the cathode. It's where reduction will happen because lead had the higher reduction potential. So if this is where reduction is happening, and it's the cathode by definition attracts cations. That's why it's called the cathode. It attracts cations. The anode attracts anions. So we know now that the lead is the substance that the cations are going to move towards, so we can cross out C and D. Now, which electrode gains mass? Well, let's consider the half reaction at the cathode. Since it's the reduction reaction, the lead 2 plus gains electrons to produce lead, and at the anode it'll be the opposite. The zinc is being oxidized to make Zn2 plus and losing 2 electrons. So which electrode gains mass? Well, the zinc electrode is a reactant, right? Zn is a reactant, while Pb is a product. Now, basic little chemistry concept here. What happens to reactants in a reaction? Well, they get used up. And what happens to products in a reaction? Well, they're being created, they're being produced. So which electrode is going to increase in mass? Well, it'll be the electrode which is a product, so Pb. So the Pb electrode is the one that the cations move towards, and the electrode that gains mass. That is correct. Okay? Choice number 10, as the cell operates, the electrons will flow to which electrode, and what happens to the voltage over time? So now we want to know what direction the electrons were traveling. Well, electrons are going to travel away from the electrode where they were being lost, right? So at the zinc electrode, oxidation was occurring. The electrons are being lost, so the electrons are leaving from the zinc electrode. The lead electrode is where electrons are being gained. That's reduction. So the electrons have to be flowing in order for reduction to occur. So the electrons are headed towards the lead electrode. So we can cross out A and C. And then what happens to the voltage over time? Well, there's a couple ways to look at that. The easiest thing to think about is that as the battery operates, it approaches equilibrium. And so as it approaches equilibrium, the voltage will eventually reach 0 volts. The whole reason the reaction is shifting in the forward direction is because it's not at equilibrium, and it has a positive cell potential. But as it operates, the concentrations of ions in the beakers change. and the reaction approaches equilibrium, and when it gets there, it'll have a 0 voltage. So the lead electrode is where the electrons flow, and the voltage is going to decrease over time. Question 11 and 12 refer to this cell. Now this is there's a half cell here which we haven't really focused on in our coronavirus teaching. So if this is June of 2020, you may be able to skip this over, but it's not that hard. On the left-hand beaker, notice there's an inert platinum electrode. Since it's inert, it's not involved in the reaction. So instead, we see there's potassium and dichromate, and it says acidified. Acidified means there's lots of hydrogen ions present, right? Acids produce hydrogen ions. So in that beaker, the potassium is going to be a spectator ion. It's the dichromate, which jumps out at me from my potentials chart in my data booklet. Dichromate has a very high reduction potential. So dichromate and hydrogen ions are in that half cell. On the right-hand beaker, there's silver ions. There's also nitrate ions, but the nitrates are going to be spectator ions, and silver metal. So we have 1 molar silver and 1 molar, 1 molar Ag plus and the silver metal. So we want the overall reaction. While looking on my chart, dichromate had the higher reduction potential. So let me just copy the half reaction from my chart. Dichromate Cr2O7, 2 minus, gains 14 electrons and adds 6 electrons. It's being reduced, and it produces 2 chromium 3 positives and 7 waters. I'm getting that directly from my chart. And then the silver is being oxidized, so we'll read the equation backwards off our chart. Silver gets oxidized to make Ag positive and loses an electron. To combine them and get the overall reaction, we'll need to multiply the second equation by 6. So now look down below at the choices. We're going to see dichromate with 14 hydrogens and 6 silver metals, the Ag, which is not Ag positive, so choice C is the correct answer. When the voltage reaches equilibrium, if you were paying attention earlier, when it reaches equilibrium, the voltage becomes 0 volts. Questions 13 and 14. As this cell operates, what happens to the mass of the nickel electrode? What happens to the concentration of copper ions? So let's look on our chart and find the 2 half reactions, nickel with nickel 2 plus, copper with copper 2 plus. I find those on my chart, and I notice that the copper is the higher reduction potential. So that tells me copper is where reduction happens, and this is the cathode. So the half reaction there is the reaction directly off my chart. Copper 2 plus gains electrons to make copper metal. The nickel is the anode. It's where oxidation happens, and its half reaction, I'll write it underneath my copper reaction. It's going to be the reverse of what's on my chart because it's oxidation. So nickel becomes nickel 2 plus and loses 2 electrons. So now that I've got the half reactions in front of me, this question becomes straightforward. So what happens to the mass of nickel? Well, look at your reaction. Nickel, the solid nickel, is a reactant. And because it's a reactant, the mass of nickel would decrease. So we can rule out C and D. What happens to the concentration of copper ions? Well, again, look at your half reaction. The copper ions, those are also reactants. And because they're reactants, their concentration will go down. So we're looking for a decrease in the mass of nickel and also a decrease in the concentration of copper ions, because both of those things are reactants in the overall reaction. What is the cell potential for the cell? Well, from my chart, the reduction potential for copper, I'm just going to grab it off the chart there, is 0.34 volts positive, and the oxidation potential for the nickel, I'll take that off my chart as well. I have to reverse the sign of its equation because I'm reading it backwards, so it'll become positive 0.34 0.24 volts. So what I'm looking for is something like 0.58 volts. Looking at the choices down here, I notice none of them say 0.58, but there's one which is 0.60. These questions came from a British Columbia website, so it's possible that their reduction potentials chart had a slightly different value for one of those two potentials. 0.60 is the closest choice. Which of these metals will react spontaneously with water? Well, we're going to do this in a similar fashion to what we did earlier. We're going to use that shortcut method of looking on our chart. These metals are all on the right-hand side of the chart, right? So calcium metal is way down here on the chart. Lead is sort of just a little bit under halfway on my chart. Mercury, I don't even think mercury is on our data booklet chart, so let's just hold off on mercury for a moment. And nickel is beneath lead. Now I can go to the internet. I've got another chart in front of me on the computer, a more detailed reduction potentials chart, and it shows mercury Hg way up here. Okay, so there's mercury. Now we're looking to see which one of these will react with water. So now if it's going to react with water, the water has to be on the left-hand side of the chart. So I'm looking on my data booklet reduction potentials table, and I can see the reaction where water is being reduced. It's down at negative 0.83 volts. And so on my chart, that would be above the calcium, but below the nickel. So the water on my chart is over here. So you remember that the pattern we established is that something on the left reacts with something on the right and below it, and the calcium and the water are following that pattern, so they're going to have a positive cell potential if you calculate it, and therefore calcium reacts with water spontaneously. If you calculate the cell potential for any of the other three, you're going to get a negative cell potential. You can also see here a limitation of multiple choice questions, because somebody who simply looks on their chart and realizes, well, we need them on opposite sides of the chart so they can see what I've done here, then they could simply use the reasoning that calcium is on one side of the water, the other three on the opposite side of the water. So on a multiple choice question, it makes sense that the calcium is likely the answer, even if you don't understand why. Number 16, consider this half reaction and balance it essentially. So go through your steps to balance a half reaction. Remember the steps we learned for acidic and basic reactions. This is not an overall reaction, just a half reaction. So the first thing I'll do is balance everything except the H's and the O's. So I'll put 2 BiO positive. Next, I'll balance the O's by putting in waters. We have 4 O's on the left, so I'll add 2 waters to the right. Now I have 4 O's on the right. Next, we'll balance the hydrogens. There's 4 on the right, so I'll add 4 hydrogen ions. That's in an acidic solution, which produces hydrogen ions. And finally, the charge. There are 2 positives on the right. Don't forget the coefficient 2. 2 positives on the right and 4 positives on the left. So I'm going to add electrons to the more positive side, and to make them equal, I'm going to add 2 electrons on the left-hand side. So this is the equation I'm looking for, and looking down here at the choices, it looks like choice C is the one that I've just created. Number 17. This is the third time we're seeing this concept. So again, we'll look on the chart. We're going to find tin, SN. Grab my data booklet. Tin is sort of here on my chart. And it says, which of the following solutions where will both ions react with tin? So the first choice, Ag positive, is up here. Well, that's going to work. Ag positive is on the left. It will react with tin because it's on the opposite side and below it. It follows that pattern. Well, where's copper 2+? Copper 2+ is about here on the chart, and that looks like it's also going to work. So that very first choice is the one that works. Nickel 2 plus is below the tin, so it doesn't work. Zinc is below tin, it doesn't work. And magnesium is below tin, it doesn't work. So silver and copper are the two that are going to give us a positive cell potential when they react with tin metal. Number 18, what happens to each carbon atom? Do they lose 2, 4, 6, or 12 electrons? Well, let's put in oxidation numbers and take a look. So we saw this earlier. There's 6 hydrogens, that's positive 6 in the alcohol on the left. There's 2 negatives in the O, so there must be 4 more negatives, so each of these carbons is negative 2. On the right, in carbon dioxide, the O's are minus 2, so this carbon is positive 4, since there's 2 O's. To go from negative 2 to positive 4 means you are losing 6 electrons, right? To go from negative 2 up to positive 4. So therefore, each carbon atom loses 6 electrons. Number 19, another balancing half reaction. See if you can do this. I confess I made several errors when I tried this myself earlier, so do it carefully. So N2O becomes NH3OH positive. So just go slowly. I was going a bit too fast myself when I did this earlier. So we have to balance everything except the H's and the O's. So I'll put a 2 in front of there to give me 2 N's. Now let's balance our O's by putting in water. Well, there's 2 O's on the right and 1 O on the left, so I'll add 1 water on the left. Now balance your H's by putting in H positive because it's an acidic solution. So therefore we have 2 H's on the left and we have 4 times 2, we have 8 H's on the right. So 8 on the right and 2 on the left, I need 6 hydrogen ions on the left. And finally the charges, there are 2 positives on the right, 2 positives, and there's 6 positives on the left. So I'm going to add the electrons, which are negative, to the more positive side, and to make the charges equal, I'll add 4 electrons on the left. So looking at the choices, it looks like choice D is the one that I want. Number 20 and 21 refer to this this voltaic cell. Which material could be used as the cathode? Notice there's actually no identity given here, but what could we use the cathode to give a cell potential of 0.46 volts? Well, I find copper on my chart, and copper on the chart has a reduction potential of 0.34 volts. So for copper, its reduction potential would be 0.34 volts. So if copper is being reduced, if it's the cathode, then that would be its potential. Now it does say that copper here has to be the anode, so therefore we want its oxidation potential, which would be negative 0.34 volts. So that's the one we actually want to use because it says it's the anode. So therefore we remember that the reduction potential over here at the cathode, we don't know that yet, when added to the oxidation potential at the anode, has to give me the cell potential. So therefore, the reduction potential plus negative 0.34 has to give me positive 0.46 volts. So therefore, the reduction potential, just solving that little equation, has to be positive 0.80 volts. Now go to your reduction potentials table and find a reduction potential of 0.8 volts. And it turns out that that is for silver with silver ions. Silver ions getting reduced to make silver metal. So silver is the choice we're looking for. What happens to the copper concentration? Well, copper is the anode, it's oxidation. So looking on my chart, I'm going to reverse the equation on my chart. Copper becomes copper 2 plus and loses 2 electrons at the anode. So because copper 2 plus is a product in that half reaction, its concentration will increase. It's going to go up because it's being produced. So we can rule out C and D. So the copper concentration will increase, and then what happens to copper? Well, copper in the half reaction is losing electrons. So copper is losing electrons, and that is oxidation, isn't it? Leo the lion. Leo losing electrons is oxidation. Leo the lion said grr, gaining electrons is reduction, right? So we want choice B, where copper 2 plus increased concentration while copper lost electrons and was oxidized. The reducing agent, number 22. This is the substance which gets oxidized, right? Reducing agent gets oxidized, and oxidation is the loss of electrons, so it's losing electrons and is oxidized. Number 23, which of the following is true? Gold does not react with 1 molar hydrochloric acid, and we get these 4 choices, which one is true. Well, I look on my chart and I find gold, and gold is on the right-hand side of the chart, and it tells me at the top of the chart that those things are reducing agents on the right-hand side, because when you read their equations backwards, they get oxidized. So gold is a reducing agent, and let's see, the very first choice, hydrogen on my chart is also on the right-hand side, but it's lower than gold, so they're both reducing agents. Is gold a weaker reducing agent than hydrogen? Well, if it's a weaker reducing agent, it means it's less easily oxidized, and that means it has a lower oxidation potential. And when I look on my chart, as I go down this table here, the oxidation potentials increase. So that very first choice, gold is a weaker reducing agent, looks correct, because gold would have the lower oxidation potential. It's going to be the one that is the weaker reducing agent than hydrogen gas. Number 24 and 25, we have some problems here because we're missing some things on our chart. We don't have the reaction for chromium 2 to chromium 3 on our chart. So let me just, where did I put my answer? Here we are. Let me just give you some information that's not on our chart. So from another more detailed reduction table, chromium 2 plus will become chromium 3 plus, being oxidized, and lose an electron. And its oxidation potential from another chart is negative 0.41 volts. So now let's see if you can finish the question. We're looking for the standard potential for this reaction, which we know is an oxidation reaction, right? The electrons are on the right-hand side. So we're looking for the oxidation potential for thallium positive. Well, we know the overall cell potential here is positive 1.19 volts, and in this equation, thallium 3 is being reduced to thallium 1, so it's actually the opposite equation of what we have here. So therefore, we can say thallium 3 plus gains 2 electrons to make thallium positive, and I just wrote the symbol wrong, and its reduction potential would be what? Well, we know the cell potential is positive 1.19 volts, so we can simply say 1.19 plus 0.41, that's going to give me 1.60, and that'll be the reduction potential. But we're looking for the oxidation potential. So I wonder if there's something wrong in this question, because the thallium 3 plus being reduced has a potential of 1.60 volts. That is correct. So technically its oxidation potential from thallium 1 to thallium 3 would be negative 1.6 volts, and I don't see that as a choice here. In any case, I'm going to think that maybe is a typo, or maybe I've done something wrong there. I'm going to move on though. I think I'm okay. Number 25, which of the following ions can be reduced by lead? And again, we have a bit of a problem because we're missing the copper 1 is not on our chart. But we can find lead on our chart, on our reduction table. Lead is sort of just under halfway, and this is the 4th time we've seen this kind of concept. Chromium 3 on our chart is, let's see, where is chromium 3? There it is. Chromium 3 is below the lead. Tin 2 plus is below the lead, and calcium is below the lead. So we can just use some logic and say none of those would react with lead, so copper 1 must react with lead. And in fact, if you look on another chart, you'll find copper plus 1 is actually up here, and that follows our pattern. Something on the left reacts with something on the right. Below it, copper plus 1 was the substance which could be reduced by lead. All right, so I hope that helps. That's a lot of review and concepts. Make sure that you can balance redox reactions. We've been balancing some half reactions here in acidic solution. Make sure you can also do that in basic solution. There's a video that on my website and posted on Edmodo for that. Make sure that you can do some titration questions as well. Those were in our worksheets that we did. Make sure you can apply the balanced equation to a titration question. And then make sure you also review electrolysis, qualitative electrolysis, what will be produced at the anode or cathode during electrolysis, as well as quantitative electrolysis, where you use the Faraday half reactions and unit multipliers, which was the last topic that we did. There are video reviews for those things as well.